So we were working on centripetal acceleration. How this acceleration is different? Why it is different? Is it different acceleration? Yes, no, maybe. A car going in a straight line, would it experience any centripetal acceleration? No. It's related to the circular path, curved path, okay, where there is a radius of curvature involved. Okay, we found a formula that's the center, and there are 2 points on the path of its circular rotation, point A, point B, point C. C is the center. We went over this, that the velocity will change direction at each and every point, and because of the change in direction of velocity, there will be acceleration, correct? If speed remains constant, there is no linear acceleration. There is only acceleration which is directed towards the center. If I put these velocities, let me call this V1, V2, are they, the magnitude wise, are they the same? V1, do they have same magnitude? If there is no tangential acceleration, yes, V1 should be equal to V2, or you can call it V. Are these 2 lengths equal as well? Right, because these are the radius. That goes through delta theta. If I put these V1s and V2 in the form of triangle, V1, V2, which are equal to each other, this is delta V. This delta V is directed to the center. This is the delta V which you could think of something, acceleration AC, which is directed to the center. It's not along the tangent. It's towards the center, okay? There is a difference between the acceleration along the tangent, acceleration towards the center. Now this triangle, if I redraw, let me call this O, P, Q, this triangle and this triangle, they both are the same triangle. They both have the same side length, delta theta, both go through the angular change of delta theta when it goes from position A to B. So these 2 are delta theta for triangle A, B, C, and delta theta for triangle P, P, O, Q. They should be the same. If I want to write delta theta in terms of this is the total arc length, delta S, this is the arc length. You do understand the difference between the arc length and the length, correct? Straight line, you do understand the difference between these 2. Arc length is going to be the curve. Since it's a circular path, this is why it's not a straight line. It is a curved line. They should be equal. Their ratios, delta V over V, they should be equal. Because both triangles, they are the 2 triangles with the equal side length, with 2 sides of equal length. We can write it as delta, leaving delta V alone, delta S over R V, delta, dividing both sides by delta T, R and V, right? We can do that mathematically, dividing both sides by time passed. Now this side, if delta T is really small, for very small value of delta T, this becomes equal to acceleration, right? Instantaneous acceleration or the acceleration at that point. Delta S over delta T, that's also approaches to V for very small time. That means this length delta, if this time is really small, so this length becomes equal to this length, and length divided by time is the speed. Delta S V square over R. That is the formula that we have here last time when I left. That tells you this acceleration, centripetal acceleration, that depends on the speed of the object. So when the speed is increased, that means more acceleration is required to keep it in a circular path. So V increases means more acceleration or more force is required. All right, and if the radius is greater, obviously it would be difficult if the acceleration is small and radius is really large. If you have a very long string attached to the stone and you are trying to move it in a circular path, it would be difficult for the stone to have, if the acceleration is small, it would be difficult for the stone to stay on the circular path with that acceleration. Acceleration should be, or more force need to be applied for to handle a stone attached with a very long string. This is the acceleration which comes from the change in velocity only in direction, no change in the magnitude of the velocity. Acceleration is always connected to the force F equal to ma. If m v square over r, that is the centripetal force that is linked to the force which is responsible for changing the direction of velocity. This is what it is, the force which is responsible for keeping it in a circular path. Is centripetal force a tension force? It can be. Is it a force of gravity? It could be. Is it what? Normal force? Yes, possible. Is it only one force? No, it could be more than one force. It really depends what is applied in that particular situation in order to keep in a circular path. So centripetal force is not a fixed force like other forces. It could be anything depending on the situation. If this acceleration, if the speed changes, what are the units for this force? Newton. All kinds of forces, they are in Newton. What's the direction of this force? Think again. What does the force depend on? So force is along the tangent line, and what is pulling it inward then? It should go along the tangent. It is pointing inward. Where the acceleration is, force depends on the acceleration. Where is this acceleration pointing to? To the center. Force is pointing to the center as well, right? The force and acceleration both are pointing to the center. Okay, it does change. The only thing this force does is it does change the direction of velocity. Every time the object intends to go along the tangent, correct? But it brings it back, put it on. The intention of the object is just to go along V1, straight line. But this force acting to the center, at every point, it brings it to the center. Okay? And it all makes sense. If it is not directed towards the center, why would it be on the circular path? There must be something pull it in. Correct? If there is no force acting inward towards the center, why would it be on the circular path? There is no reason for it. So it is always pointing to the center. Acceleration is also pointing to the center. Now what if the speed changes too? What is this motion called where the speed remains constant but velocity changes? Does this circular motion have a name? Uniform circular motion. If the speed changes, then it is the non-uniform circular motion. Initially, for centripetal acceleration, speed does not change. It's a uniform circular motion. But if the speed, now there is no restriction, anything could go faster or slower on a circular path. If there is some external agent constantly pushing it, yes, it can accelerate or it could decelerate. In that case, there will be a non-uniform circular motion. The acceleration, if the speed changes, then there will be tangential acceleration as well. One acceleration would be, if I draw with a different color, one acceleration would be in the direction where along the tangent, one acceleration would be towards this is T, this is C. There will be two acceleration produced. Where does the AC come from? AC due to change in direction. Where does the AT come from? Due to change in magnitude. Okay. When I mention speed here, I truly mean that we are talking about the magnitude. Okay. We are talking about something, for example, it was rotating at 10 meters per second. It has gone up to 10 meters per second now. Something like that. The number has changed. In this case, the number does not have to change. It's only due to the change in direction of velocity. These two accelerations, when we put them together, can we find the resultant? What should I do to this? We can find the resultant, correct? How would we find that? A would be equal to AT square plus AC square. That would be your final. And if you want to know what angle, it would be directed at AT over AC. So it would be somewhere in between the final acceleration. It's not going to be exactly towards the center. It's not going to be, if it's speeding too much, tangential acceleration is very strong, it would be leaning more towards the tangential acceleration, correct? If the speed is not changing that much by a very small value, it would be leaning more towards the center, okay? But what is most important here to remember, okay, that's where most of the time students do not know the difference between the change in magnitude and change in direction, or the difference between AC and A tangential. A tangential is only related to when the speed changes. Okay, that means it's getting faster or it's getting slower. All right. AC has nothing to do with anything going faster or slower. Okay, AC is generated due to change in direction of velocity. Yes.
So what if the accelerator at is very fast as tangential, but AC is the acceleration of
Change in direction of velocity.
okay, what is that what we're about to
So tangentials are always going to be along the arc length, right? These are ACs, or the forces, they are pointing inward. Okay, the tangentials are only coming, the tangentials and the linear acceleration, they are the same thing. Okay, so if you have a picture having a tangential acceleration and linear acceleration, two different things in your mind, they are not the different thing. These are the same thing. If it would go straight, if there is no central force, it would go straight, what would be its linear acceleration or what would be its linear velocity? So on the ends or edges, it's just the linear velocity. All motions, all circular motions, they do have a linear component to them. Right? You remember you did an experiment, I think it was Atwood machine. So in Atwood machine, you had a pulley attached to a sensor, and the pulley was giving you what? It was rolling for sure, but did it give you a rotational speed or rotational acceleration? Did it? It was there, but did you measure that one? What did you measure? You measured the linear speed. If you go back and think about that lab, you measured this. V versus linear speed versus time. And the slope of that line was linear acceleration. Every rotational object, it does have a rotational, or it does have a linear component to it. That only means that what is each point can do linearly. Good. Should we move on? Confused enough? When we talk about a rotational motion, we also talk about the number of times it's been done. Frequency, the number of revolutions per second. Now revolutions, cycle, round trip, a very simple term, but in revolutions or cycles, they are more commonly used to define the frequencies. The total number of, so if it starts from here, it completed 1 revolution, 2 revolution, you have done the simple pendulum. That is one complete round trip. That is the number of cycles per second. That is defined as the frequency. It only tells you how fast your object is going. If the frequency is greater, if it is like 10 per second, that means it's going to go 10 times in a circle in 1 second. Frequency is inversely, the more cycles you have, the less time you have to do 1 cycle. Is that correct? The more cycles you have, the less time for 1 cycle. Is that right? If you have 3 cycles per second, and then 8 cycles, which one has more time to complete 1 cycle? No. Within the same time, so it's like you have this region, you have 3 cycles there. 1, 2, 2, oh my gosh, 2 and then 3. So if you have 3 cycles, there is some time linked to each cycle. If I make 8 cycles, I shouldn't have picked 8 here. Now I have to make 8 cycles there. Which one you think seems like taking less time? Within the same region, now you have packed more cycles in there. So the time would reduce. For one, this is 1/3 of a second. This is 1/8 of a second. The wavelength will change too. The time period will change too. The frequency is inversely proportional. Time period is time to do one cycle or revolution, and it is inversely proportional frequency. Greater the frequency is, less is the time to do one cycle. It's just going to go very fast, very fast. Time will be small, and you can follow these examples. If you have squeezed in the same space, if you have squeezed more revolutions, it would just going to make it go so fast, so many cycles, and it would reduce the time for each cycle. So, and wavelength is reduced too. Okay, wavelength is reduced, and I don't know if you already know about wavelength or not, but wavelength is nothing but how long this is. Okay, let's quickly do a problem involving the time period. Yes, T is the time period, lowercase f is the frequency. The units for frequencies, that is 1/second. Revolution doesn't have a unit per second, or you could define it as also one common one is the hertz. That is after the name of a scientist. All physics units, they are after the name of the scientist. And time should be in seconds. You plug in 1/1s, that's going to be s, right? Time is always in seconds. No other units defined for time. So if you have a 150-gram ball attached to the end of the string, revolving uniformly in a horizontal circle of radius 0.6 meter, the ball reaches 2 revolutions per second. So you have a 150-gram and the radius is 0.600 meter. It is revolving in a horizontal circle, not the vertical circle, horizontal flat circle. And it does 2 revolutions per second. So frequency is 2 revolutions per second. It doesn't look like a circle, but it is a circle. Okay? It is a circle. It's same 0.6 everywhere. What we want to know, what is the centripetal acceleration acting on that stone which is attached to the string. This is string of the negligible mass. Can you find it? For centripetal acceleration, you need V, right? Do you have V given? Is V given? How fast it is going, it's not given. Can you find it? Radius is given. Frequency is given. Yeah. And? Yeah. That is the total distance covered in one cycle. Correct? Do we know the time for one cycle? Yes. If there are 2 revolutions per second, that means it's going to be 0.5 seconds time period. This is not the plain T, it is capital T. 2 times 3.14 times 0.600 divided by 0.5 seconds. So there are 2 things that you are using in it. One is the knowledge of time period. Okay, how do you find the time period when the frequency is given? One way is just to get some up. Obviously, if it is 2 revolutions per second, that means in each second there are 2 revolutions. One cycle would be done in half of this time, right? Half of a second, 0.5. So, or you could do T is equal to 1 over 2, which is 0.5 second. Both ways. So the one thing you are looking into finding the time period, also getting some idea how you can relate the distance with the speed. Once you know V, can you find centripetal acceleration? Yes. You know everything. You know speed, you just plug it in, you have to square it, divide it by the radius, and that would give you the centripetal acceleration. Period, yes. Not time at any instant, no. Sorry? Yes. Good. Move on. What an ugly car. But the car is on the road negotiating a curve, and the radius of curvature distance at that moment from some center. Now this circular path not always have to be excellent circle or complete circle. What we are interested in, there should be, if it is curving, there should be a center around which it is curving. The frictional the weight force and the normal force. So I'm not going to draw the weight force and the normal force in the direction I usually do. But for you, towards the road is the weight force. Above the road is the normal force. So they should be balanced with each other because the car is not really accelerating in upward or downward direction. So the normal force, all the time when you are driving the car, the normal force is balanced with the weight force. It's a friction between the tires which is constantly changing. Acceleration is changing depending on how you accelerate or decelerate your car. The friction force would be acting towards the center. All 4 tires, if they all are rolling, if they all are rolling, they should provide 4 times the static friction. Now the rolling friction is the static friction. Now this is one of the concepts that would come later again. But usually rolling friction, you can confuse it with the sliding friction because it's moving. So you might think it's a kinetic friction or something is moving, it's less than the static friction. Rolling friction is not a kinetic or sliding friction. It is the moment the tire is in contact with the road, it is at rest. Okay, so this rolling friction, it is indeed a static kind of friction because the point on the tire is at rest for that moment with the road. So static friction for all, you can add these are 4 times the static friction from each tire that would be acting towards the center. It will slide away from that curve. You won't be able to keep it on that circle. And this is a flat road. Okay, this road is flat. What other ways you could think of if the road is, if the friction is not enough, what other ways you might think of keeping the car on track? Sorry? Have you ever noticed some of the highways or the exits are banked? Why are they banked? When friction could exist with the banking, but banking purpose is to produce friction towards the center. Okay, the purpose, produce centripetal acceleration towards the center. So the other way could be, if it's not a flat road, if you make it a banked highway, that could also be a reason to keep it at the circular path. I am going to do friction example in the class. I'm going to give you the banked highway to do on your own. Okay, but don't miss it. If you don't understand it when you do it yourself, then come back and discuss that with me. But don't miss that point because this is the part of it. Part 1 is when friction is keeping it at the curve. Second is when the banked highway or the banked road is responsible to provide the necessary centripetal acceleration. So if the frictions are producing, that means Fs should be equal to mv square over r. Is that right? That's the only force acting on the car. In that direction, we know there is a forward too, there are other forces, but in that direction it's only the friction force. Friction force is equal to mu s mg mv square over r. So your static friction providing acceleration to the center, or this, there is one step, I think, let me add that. There is net forces in that direction that would be equal to mv square r, and the net force is the friction force. M gets cancelled. V square would be equal to mu s r g, if I square root it, mu s r g. Good. It's not dependent on mass, so it doesn't matter how heavy or how light the car is. The most important thing in order to keep the car on that curve is mu s should be enough. Okay, r and g value, that should be constant for that location, but r and mu s, they are the ones which are controlling the speed of the car on that road. If the r is greater, v would be greater too. Okay, if this is a constant between it, it has to go higher in order to keep it on track. So these values adjust with each other. So velocity will adjust accordingly with these two values to keep it, to provide it necessary, okay, or the what it needs to be on that path. That is in case if you have a flat road and the friction is only responsible to keep it at the center. On the banked highway, you will have obviously the resultant would be a different equation. It's not going to be as simple as this one. And the picture is, let me draw that. If the highway is banked and no friction, it is possible to have both, but you will solve for the situation when there is no friction present between the tires and the road, but the highway is banked. That's the back side of your car. Okay, it's going on the curve and you're looking at the car. You see two tires only, the back tires. Normal force is upward. Gravity force is downward. Oh, this is theta. This angle is also going to be theta, and this is also theta. Dividing normal force into its components, this is n cosine of theta, n sine of theta. Cosine of theta. This is n sine of theta. Here the normal force is divided into its components, okay, because the car is not sliding down or up the hill. It is going straight. So it's a normal force component which is responsible for providing. So there is a circular path. That's the radius towards it. Normal force, one component of the normal force which provide the centripetal acceleration or centripetal force to keep it at the center. So you will work on it yourself, take the horizontal forces. This picture is complete here. You need to take the horizontal forces, balance them with each other, mg and n cosine of theta. You will take the horizontal forces, which is the centripetal force, and this component which is also acting to the left. Take them, set them equal to each other and see if you can get the form. You are not going to get a number because I didn't provide you any number, but you are going to get an equation, something like that. Get an equation for velocity in terms of velocity will include is rg tan of theta. Square root rg tangent of theta. Since this time the friction is not involved, you don't have the friction coefficient in there, but you do have the radius. Higher the radius, more speed is required, g and tangent of theta. Okay, I will check with you if you did it or not, but this can be easily the part of the exam, even the derivation. Questions? When you solve this, see how you can get that. There is just one last thing. I think I would like to do it with centripetal acceleration. So we'll do the law of gravitation and the Kepler's law in next lecture, and that ends the chapter. You have a vertical circle. Let's say you have a bucket. Bucket is attached to a rope. You are moving that bucket up and down. It is a vertical circle. It's not a horizontal circle. So you have a rope or string attached to it. Let's consider it does not have a mass. Mass is 0.150 grams. The radius is 1.10 meter. The question is, what is the tension or speed? What is the minimum speed at the top? And what is the tension at the bottom position? So you have a mass attached with the negligible mass rope, and you are moving it in a vertical circle. There are two positions defined for you. Okay, there are other positions too, but two positions defined. Let's call this position A, position B. You want to know what is the speed, what's the minimum speed required in a circular path, what's the tension required for the bottom to keep it going in a circular path. Could someone tell me what direction I should draw on for the friction, the tension? For the bottom. Okay, let's start with the top one. Correct? From the point away. And what else is there? mg is in the same direction too. On this position, this is mg and tension is upward. Which position do you think? Is tension same the whole time? Should tension stay the same whole time? What would be your idea? So basically your rope should have the same stiffness throughout. Great. Yes, it should be lower at the top. Why? Because there is already a force giving it a centripetal force, which is mg. In the bottom, it's pushing down more on it, so tension increases at the bottom. Okay, so tension is not the same throughout the motion. At the top position, so for part A, we can do minus t, let me do the sum of forces like we always do. And m, A, forces are negative t, negative mg, negative mv square over r. Because the acceleration is the centripetal acceleration this time, you already know what that acceleration is, and that is v square over r. T plus mg mv square over r. So you said that the tension should be the lowest. Yes, it should be the lowest, but how low it could be? If we want to know what is this minimum speed, because the requirement is what's the minimum speed in order to keep it going in a circular path, we can set up as a limit t equal to 0. But the tension would be greater than that, because at tension 0 means it won't be stiff, it would go limp, it cannot stay in a circular path. But as a limit, if we set t equal to 0, mg equal to m v square over r, v is equal to r g square root. If we plug in r here, if we plug in g here, that would give us, remember this is not the speed that it should be on there. This is the minimum speed. Below that, it's not possible because the tension is 0. The actual value for tension should be greater, little bit greater than that, and speed will be little bit greater than that too. For the second part, the same equation, T is positive, mg is negative, this is positive, tension will be equal to mg plus m v square over r. You can plug in the mass value, you can plug in, here. So, okay, make it V2. This is V1 because the V's are not the same. It moves slow. It moves slowly at the top and faster at the bottom. So solve for if V2, let's say, is equal to V1. Find the value. So there's some work I'm leaving for you. You will find this V minimum by using the radius. Multiply that V minimum at the top position by 2 to get the speed at the bottom. So V2 at the bottom is higher than the V1 at the top, and it's almost twice the value. This is given to you as well. That's a part of the problem. Okay, it's not a known fact. It's given to you as a part of the problem, and you can use the value of V2 in the equation, solve for tension. There's a lot of things for you to go over when you go home today. A lot of concept introduced, okay, with the centripetal acceleration, Newton laws plus the normal tension, all these forces. Please take your quiz with you.